So last time, like I was emphasizing, we said we get to calculate the number of moles by what? What do we get to use when we're dealing with the number of moles? What do you use when calculating? So we said number of moles basically, you're trying to look at the, okay, something like this. When I'm given, for example, a formula of carbon dioxide, you're given the mass, and then they also give you the molar mass. Of course, the molar mass is something that is determined, alright? So the number of moles in such cases is mass over what? Molar mass. That's what I said. Then apart from that, we also said we can also determine the number of moles by dealing with our concentration. Well, we know concentration is the number of moles dissolved in a liter or in a volume of a solution. In a case where your units for the volume is in liters and you have your number of moles there, this is specifically called what? Molar concentration or molality, presented by capital letter M, which is also just one way of expressing our what? Our concentration. Okay. So the number of moles in this case is given as the product of your concentration and volume, and I emphasize to say make sure that your units are matching. In a case where you've been given a concentration in terms of mole, for example, per cubic meters, you want to make sure that your given volume should also be in what? In cubic meters, so that they cancel out and then you get to remain with what? The number of moles. That's very, very important. Okay. Now, this afternoon, we want to take a step and basically gets to talk about combustion analysis, back titration, and also just the application of everything that has been covered, being able to determine the number of molecules, the number of atoms in a given substance. Then just before that, I also need to highlight something that is very important just before we get to move on, so that I may avoid the issue of forgetting. Okay. So there's also an aspect that requires you people to understand the conversions from the units that are used on the periodic table. So I said the units that are used for our molar masses is atomic mass unit, right? So now you need to understand as a chemist how to convert from atomic mass units to grams. Are we together? Because in some of the cases in different topics, they are going to give you your masses in terms of atomic mass units. But as you are doing your calculations, you need to be very careful. Especially I like giving an example of this question that came last year, where they ask you to determine the de Broglie wavelength, where you know this is your formula, right? And then they tell you, they give you a mass of 4.00 atomic mass units as your mass. Then they also give you the velocity. So now the mistake that students get to make is they are going to think that, okay, I have my mass, I have the velocity, just plug it into the formula. That doesn't work. You need to convert the atomic mass units to what? To grams, to kilograms, sorry. Okay, so how do you get to do that, ladies and gentlemen? So I emphasize to say, when you look at an atomic mass unit, you need to understand that it is just basically one. So one atomic mass unit is a very small mass. So it's 1 over Avogadro's constant in grams. Okay, so if you get your calculator, divide the Avogadro's constant, of course in brackets, divide it into a 1, you are going to get something like this, 1.0667 times 10 to the power, I don't know, negative what? Is it negative 24? You can try that out. So that gives us the mass in what? In grams. So this is the ratio that you get to know, implying that if you're given 4 atomic mass units, you can just multiply the other side by 4, this side by 4, then you'll be able to get what? You'll be able to get your answer in grams. Then you know to move from grams to kilograms, you can just divide by 1000, right? Then you'll be able to get your solution in kilograms. That is also something that is very important that I needed to mention before we can proceed to where we are going. Any questions about that?
Is that figure given in the question paper, or just have to know it?
You have to know it. Like, the easiest way to remember it, madam, is the good part is you know that you already know the Avogadro's constant. So it's just 1 over the Avogadro's constant. You can just do that. Just this is going to be given, of course. The Avogadro's constant is going to be given. So you can just divide the Avogadro's constant into a 1. You'll be able to get your conversion factor. That's easy to remember, right?
Alright, thank you very much.
Okay, so now, said we're proceeding to the idea of talking about combustion analysis. So I don't want to talk about the basic part of which I know you don't have challenges with. So in a normal case, ladies and gentlemen, where we've given you a formula, let's say you're given a compound that is consists of 3 different elements, carbon, hydrogen, and nitrogen. Then they give you the masses in which they do exist, or even just sometimes they may not give you the mass, they may give you the percentage, maybe carbon 60%, hydrogen maybe 10%. So you guess that the other is going to be 30%. So they ask you to find out the formula in such a case. So you will need to consider the percentages to be your masses, and then you come up with your molar masses, which are coming from the periodic table. Okay, something like that. So that is like your periodic table. These are the molar masses. Of course, they're just I'm just trying to approximate the values here. So now you can, considering your percentages to be your masses, you can divide the molar masses into the masses to give you the moles, right? For all these elements. And then what we know at this stage is you can divide by the least. Divide by the least number of moles. Let's take an assumption to say this is giving us 5, that is giving us 10, and maybe that is giving us 2.5. So you need to divide by the least, which in this case is 2.5. And if you divide by the least number of moles, you are going to have 1, you have 4, and then you have 2. Okay, so that gives you now what we call the empirical formula, right? Empirical formula. Okay, so that is something that we already know. We've been looking at this from high school. Now I'm sure there are no challenges there, there are no questions. So now at this point we need to use a different method or a different technique to help us find the masses of these elements contained in a specific what? Compound. So under combustion analysis, basically we get to focus more on carbon, hydrogen, and oxygen containing compounds. Okay, so combustion analysis, ladies and gentlemen, involves you burning either a hydrocarbon or a carbon, hydrogen, and oxygen containing compound being combusted or being burnt in oxygen to give us carbon dioxide and what? And water as our products. So in such a case, what they're going to do is they're going to give you the mass of a compound of a known formula, which in this case have given us to be 2.00 grams. Then they'll give us the amount of products. In this case, we've told carbon dioxide 4.86. Our water is 2.03 grams. Okay, so find its empirical formula. If it only contained carbon, hydrogen, and what? And oxygen. So how do we get to this? How do we get to such a question? What are we supposed to do? So remember, we've been given the information about the compound. We've been told it contains carbon, hydrogen. So the fact that we already know the elements and we already know their molar masses, which are found on the periodic table, all we just have to do is find the individual masses of what? These elements, carbon, hydrogen, and oxygen there. And we get to do that by coming up with a ratio, the ratio of the molar masses. Okay, I would go to my carbon dioxide. I'm interested in finding the mass of carbon. Okay, since I've been given the mass of the entire carbon dioxide, now I need to ask myself a question: how many carbon atoms are in the carbon dioxide? Because this is one, so it's a carbon over what? Over your carbon dioxide. Multiply by what? We need to multiply by the total mass of the compound. So we are using the ratio, this ratio, to help us find the mass of carbon. Okay, carbon in the carbon dioxide. So what is the molar mass of carbon there? It's 12.01. What is the molar mass of carbon dioxide? The relative molecular mass. So by the way, when you see this relative molecular mass, it tells you that you need to add the relative atomic masses of the elements, of the atoms contained in a compound. So this one would involve you adding for the carbon and the two oxygen atoms, which is going to give us something like 44 point what? You people with calculators. I said every time we have class. Yes? I hope you people are following and we are on the same page. You're just too quiet.
You're following. You're following.
Okay. So what are you getting as your relative molecular mass of carbon dioxide?
4.01.
Okay. So I can even remove this because I've already displayed it the other side, right? I've already shown it. So what are we going to get now as our mass of carbon dioxide? Of carbon, sorry. What's carbon dioxide? Okay. So for our carbon we have 1.33 grams. We can also find for hydrogen. Now, this is the tricky part. I remember mistakes where it's. Look at this one. How many hydrogen atoms do we have? We have 2. How many? Then the total thing is what? H2O, right? So multiply by the mass. So now, subst the relative atomic masses. For hydrogen, it is 1.008. So that is multiplied by 2. Then on the denominator part, we're going to have the same, representing the hydrogen, the 2 hydrogen atoms, plus for oxygen, which is relatively 18 point something. Help me.
18.016.
So 18 point what?
016.
Then for the top part, 1.008 times 2 is what?
2.0.
So what are we getting as the mass of our hydrogen? What do we have?
0.22.
Okay, so now, ladies and gentlemen, which one are we going to use? Are we going to use the carbon dioxide or water to help us find the mass of oxygen? Which one are we going to use between the two? Anyone to help us? Okay, I like that. So it's saying we need to add the masses of carbon, hydrogen contained in the compound of a known formula, of which we are given the total mass, right? So we just have to add the 2 and then subtract from the total to help us get the difference. Now, why do you think, why are we not using either carbon dioxide? No, why aren't we using the 2? Carbon dioxide and water. But we do have the oxygen there. Why aren't we using the same procedure? What do you think?
Maybe because the oxygen is in excess, because also using it to burn the compound.
Okay. So thank you very much, Ma, for that. What I would say is this: if you look at this oxygen, the oxygen contained in the carbon dioxide and in water there is not basically is not only representing the oxygen, so it would make us over exaggerate the mass of oxygen actually available. Okay. All right. So we can add the two. 1.33 plus 0.23. Subtract that from 2. So I'm getting a value of 0.44 grams. I hope these values are okay because I already know the answer. So we have our
I'm waiting. Stop waiting.
I'm still calculating. Okay, so for carbon to be 0.11.
so it's advisable to basically indicate 4 significant figures.
Okay, so 0.1107. Then for hydrogen to be 0.2282.
Mm-hmm.
Then for oxygen 0.02750.
Some 8 points.
2982.
2982. Let's take two significant figures. 8.3.
So 0.03.
4 points. So 4.0 is fine. Um, So, are you basing your question part where we were
the masses of why the resolution is H2. Now to find the moles of why the resolution, why did we use the moles of the same why the resolution instead of multiplying by 2?
Okay, so whenever we are trying to determine the number of moles for all these constituents elements in the compound, we don't basically look at it to be the atomic, because we basically don't know the number of hydrogen atoms that are in this compound. Okay, we don't know, except we look at the exact number of the atoms when we are looking at the issue of finding the masses on the other side, because at least we are aware when we are talking about water we can say there are two. Now you can't say even in this one there are two. No, that is wrong. Then what's the point of you finding a formula? Just get for a single one, so that we can find the number of moles to help us find the exact number of hydrogen atoms in the compound. We don't get to use the atomic yeah.
Right.
Let's look at back titration as our last thing this afternoon. What do we know about back titration? So yeah, what is back titration? What is back titration? What is titration?
So we move to back titration after titration.
or the best thing that I can tell you is make sure your value of x should always be what? An exact a whole number. It shouldn't be a decimal number. Are we together? So now, in such a case, if you can try any value in between the two, you can get the average value of the range and try to find the value of x there. Yeah, then after trying to find the value of x, then take it as a whole number. Okay. Yeah, it should be somewhere there. Is that okay?
Yes.
All right. So back titration involves you reacting. So back titration is just like the difference with back titration is you already know the formula of the compound. Now back titration is more involved, like unlike combustion analysis, which is helping us find the formula. For back titration we get to find the concentration. Okay, we are more interested in finding the concentration, so we're trying to use concentrations of acids and bases to help us find more information about a substance that is unknown. For example, if you look at this question, the mass of magnesium hydroxide in an injection tablet was determined using this procedure. So the tablet was crushed and dissolved in exactly so you dissolve it into an acid. Then after dissolving it and reacting it with an acid, you get the excess and then react it in. You get the excess acid, react it in the second reaction with a base.
which is the neutralization reaction. After that, you get to use the information now to find what? More details about the magnesium hydroxide. So a basic idea is this. In this reaction, we don't know much information about this thing here. We don't know much information about it. The question